Okay, so here's the key to the practice worksheet on continuity. So number 1 says, given the piecewise function below, determine the values for which the function is discontinuous. So we're looking for point discontinuity, and there's that test we can use. Then classify each discontinuity as a removable or non-removable, and we have two types. We have infinite, if there's an asymptote, and we have jump. You must justify your answers and show all work to receive credit. So the key places are to look are where there's breaks in the domain, so at 3 and 4, but also where there's breaks in the domain here in the restrictions in the domain. So first of all, we'll start with 2. So let's consider x equal 2. So continuity test would be, does f of 2 exist? So if I want to apply f of 2, I've got to use this function because x is less than 3, 2 is less than 3, so I have to plug it in here, and I can see that I'm going to have 4 take away 3 over 0, so f of 2 does not exist. So I immediately know that it's discontinuous at x equal 2. And from the left and the right, if I wanted to look at the limit, even though I already know it's discontinuous, but I want to know the type. So if I look from the left, I'm going to have 2 into the top would give me a positive 1. A small number to the left of 2 would give me a small negative. So we would be heading to negative infinity. But from the right, you can put 2 directly in the numerator, so you get 1 again, over a small 2 from the right, a small number 2.0001 would be a small positive, and that would be positive infinity. So that lets me know that at 2, and the factor doesn't cancel, we have it's discontinuous at x equal 2. And the type of continuity, it's non-removable. And it's of the infinite type. There's asymptote, vertical asymptote. All right. Second, let's take a look at 3. So first we have to say, does f of 3 exist? Well, we're supposed to use the second function piece if x is between 3 and 4, and you're including 3. So that would be sine of 3 pi, and we know that sine of 3 pi is the same thing as sine of pi, and that is 0. So it exists. Okay, then the limit as x approaches 3 from the left, that means smaller than 3, so that would be this one. I'm going to put 3 in there, so that would be 3 squared minus 3 over 3 minus 2. That's 6. But the limit as x approaches 3 from the right, I would have to use this middle function, so that's sine of 3 pi, and we found that. If I put pi in there for x, then that's 0. So the limit as x approaches 3 of f of x does not exist, and so that's discontinuous there. So what type of discontinuity is? Well, if you're heading towards 6 from the left and 0 from the right, that's going to be a jump discontinuity. Okay, and then the third discontinuity we might have to try is 4. So when x is 4, this is 4, this is x is 2, checking that, and this is x is 3. When x is 4, we have to say, does it exist? So f of 4, when x is greater or equal to 4, use that one, and the natural log of 4 take away 3 over e to the 4 plus 2. That's going to be a large number, but I don't really need it because we end up getting the natural log of 1 in the numerator, and the log of 1, no matter what type of log, what base it is always going to be 0. So this is 0 over some number, which is 0. All right, so it exists. But now I have to see if the limit exists. So the limit as x approaches 4 from the left, that means we're going to use sine. So that's sine of 4 pi. Sine of 4 pi is 0. And from the right, the limit as x approaches 4 from the right, we would use that equation there, and that's the natural log of 4, take away 3 over e to the 4 plus 2, which we just calculated it as 0. So the limit exists as x approaches 4. And then the third thing is the limit as x approaches 4 of f of x has to equal f of 4, and they both equal 0. So it is continuous at x equal 4. So the only points of discontinuity are x equal 2 and x equal 3. And those are my reasons up there. And I just realized one more thing. I did check this denominator, but I didn't check this denominator, and I did, but you may be wondering. So this denominator cannot equal 0, right? We know that denominators can't equal 0, but if I solve this, I get e to the x is equal to negative 2. And there are no values of x that would ever make that true. So this denominator right here doesn't have any restrictions, and that's why I didn't mention that one. Okay, the second one, given the graph, determine if the graph is continuous at specific values of x. So again, we're looking at point discontinuity. If the function is discontinuous at that x value, explain which part of the definition of continuity it does not meet, then classify it as removable or non-removable. So again, we will go through the continuity test. So number 1, does f of negative 7 exist? And when x is negative 7, y is 7. So it exists. Next, we have to see if the limit of the function as x approaches negative 7 exists. And from the left, it's heading towards 4. And from the right, it's also heading towards 4. So step 2, the limit as x approaches negative 7 of f of x exists. So that's not the problem. But then 3, we know that f of negative 7 has to equal the limit as x approaches negative 7, and it does not. So that's why it is discontinuous at x equals 7. And what kind is it? Well, if you turn this function into a piecewise function and you say, well, let's let, when x is negative 7, let's let f of negative 7 equals 7, then you've removed the discontinuity. All right, let's take a look at x equal negative 3. And f of negative 3, there's a hole here and there's a hole there, so it does not exist. So that was an easy one. Therefore, it's discontinuous at x equal 3. And what type of discontinuity? We see it's a jump. And then the last one, at x equals 3, which is right here. Let's do the test. So f of 3, does it exist? Yes, it does. It is negative 4. Okay, does the limit exist? Well, the limit as x approaches 3 from the left is headed towards negative 4. But the limit as x approaches 3 from the right is headed towards positive infinity, which means that's an asymptote. Okay, so the limit does not exist as x approaches 3. So it's discontinuous. And the type of discontinuity is infinite because there's a vertical asymptote which comes from that right here. Excuse me. Okay, so number 3 says use the coordinate plane below to graph the function with the following characteristic. It has a removable discontinuity at x equal 2, which means that's going to show up like a hole. So I'm going to go ahead at x equal -2, and the limit exists, remember, so I'm going to put a hole here and maybe a point up here at x equal -2. In an infinite non-removable discontinuity at x equal 1, which is another way of saying there is an asymptote, vertical asymptote right there at x equal 1. And then a jump non-removable discontinuity at x equals 5. So that means the limits are heading to different directions. So I'm going to put something here and something here. Okay, so this jump discontinuity at x equals 5 would be something like this. And maybe this goes down to negative. So that's a jump discontinuity at x equal 5. And this an infinite non-removable discontinuity, well, I've already got this, and I'll have this one go in the opposite towards positive infinity. They could go in the same direction, but then it would mess me up here. All right, now this last part, this jump discontinuity, oh, see, I don't like that. That wouldn't be a function. So let's make this go this way because I don't want to break the vertical line rule. Okay, so because see, I need this limit to exist if I want it to be removable. So, in fact, I don't want that there. Let's see. I want this limit to exist. Okay, so it has to exist from the left and the right. It has to be headed towards the same value. There we go. Right. And all I need, I can't have that because then it would cease to be a function. So for a removable discontinuity, all you want to do is have a hole and then put a point there where you could plug that hole with that redefined point there. So that's my graph with those 3 discontinuities. Okay, so this last one, it's not really about discontinuity. It's about what does it mean for a limit to exist. So first I look at this function and I see I can pull out an x. So that's what I'm going to do. All right, so pull out an x and I'm left with x times x squared plus bx plus 12. And that is good news because that's quadratic. So if we understand what it means for a limit to exist, we know that this x minus 3 denominator is giving us the trouble because when we put 3 in, you get 0 at the bottom. So since this is quadratic, I can be clever and say, well, if I get rid of this x minus 3, then the limit's going to exist. So that's how I knew it's going to be x times x minus 3. And then where does x minus 4 come from? Well, I want the numbers here to multiply to be a positive 12. So that's how I knew it would be x minus 4. So then to find out what b is, I just multiply that out. And I get x times x squared minus 7x plus 12 over x minus 3. And therefore, b has to be -7. Okay, and the last one, going to take a little while. Determine the values of a and b, which would make this piecewise function continuous everywhere. So if we look really quickly, we see that the issues are happening at 2. You can have a left-hand limit and a right-hand limit. And at 3, a left-hand limit and a right-hand limit. You want all those limits to exist and be equal to their left and right-hand side if we want this to be continuous, right? So that's where we're going to start checking. So first thing I notice is I can factor that top function. That's going to be x plus 2, x minus 2 over x minus 2, and those cancel. So this function is going to look like x plus 2 when x is less than 2. And this function is going to look like ax squared minus bx plus 3 when x is greater than or equal to 2 and less than 3. So I want the left-hand limits to equal the right-hand limits. So the limit as x approaches 2 from the left, I'm going to use this equation, which is nice because I can just direct substitute and get 4. So now I know that the limit as x approaches 2 from the right of ax squared minus bx plus 3 should equal 4. Okay, so how do I find that limit? Well, this is a polynomial. I can just direct substitute 2 in there. So when I do, I get a times 2 squared is 4 minus b times 2 plus 3 equals 4. Okay, so I have two unknowns, 4a minus 2b equals 1. All right, so I know that's true. This is tricky, but I'm stuck because I have two unknowns. But luckily, I have another left-hand, right-hand situation here with this 3. Okay, so I'm going to do the same thing. I know that the left-hand limit, as x approaches 3 from the left, I want it to be continuous. It has to exist. The limit as x approaches 3 has to exist. In order for it to exist, the left-hand limit has to equal the right-hand limit. Okay, now, so the limit as x approaches 3 from the left, I would use this equation, ax squared minus bx plus 3. And the limit as x approaches 3 from the right, I would use this equation. Now, you have to understand that a and b are just numbers. We just don't know them. So this is a polynomial, this is a polynomial. We know it's continuous, so I can direct substitute. So I'm going to put 3 in and see what we get. So we have a times 3 squared, which is 9, minus b times 3 plus 3 is supposed to equal 2 times 3 minus a plus b. So that gives me 9a minus 3b plus 3 equals 6 minus a plus b. All right, if I add a, I get 10a. If I subtract b, I get minus 4b. And if I move this 3 over, I get 3. And what do I have now? I have a system. So now I can solve this system. I'm going to use elimination. That's my system, and I'm going to multiply the top equation by negative 2, so I like to get opposites. So that gives me negative 8a plus 4b equals negative 2, and 10a minus 4b equals 3. So that gives me 2a equals 1. Solving for a, I divide by 2, and I get a is 1/2. All right, so once I have a, I can just plug a back into the system, so that's 4 times 1/2. Just pick up an equation, doesn't matter which one. I'm picking the top one. So that's 2 minus 2b equals 1. That's negative 2b equals negative 1. Divide by negative 2, and b also equals 1/2. That's kind of a coincidence. So we found the values of a and b. Now, it's a fun exercise to check this. So I'll just put these a's and b's, and this will give you an extra problem to check. Prove that a 1/2 and b 1/2 is going to work. It's going to make this function continuous everywhere. So x squared minus 4 over x minus 2 when x is less than 2, and 1/2 x squared minus 1/2 x plus 3 when x is between 2 and 3, and 2x minus 1/2 plus 1/2, which ends up just being 2x. See if that function is continuous everywhere. I did it here. So I found out that f of 2 exists, I found that the limit exists, and I found that they equal each other. And then I found out that 3 exists, f of 3 exists, and the f of 3 exists, and I found out that they equal each other. So it was a good exercise to check.